Ever wondered what makes space solar panels so efficient? It's not your typical rooftop silicon. Instead, a hidden hero, germanium, powers satellites, Mars rovers, and deep space probes. But why germanium? Let's dive in. To understand germanium's role, we need to talk about multi-junction solar cells. Unlike ordinary silicon panels, which absorb only part of the sunlight's energy, multi-junction cells stack several layers, each tuned to capture a different part of the spectrum. This layering pushes efficiency beyond 30%, nearly double that of standard solar panels. At the base, germanium has a dual role. It absorbs low-energy infrared light while providing the structural and electrical support for the entire cell. In the middle, gallium arsenide captures visible light, covering the broadest range of the spectrum. At the top, gallium indium phosphide absorbs high-energy blue and ultraviolet light. Picture it like this. A beam of sunlight strikes a multi-junction solar cell. The most energetic photons, blue and ultraviolet light, are captured by the top layer. As light travels deeper, visible wavelengths are absorbed by the middle layer. Finally, infrared light reaches the germanium base, ensuring no part of the spectrum is wasted. This layered absorption maximizes efficiency, making multi-junction cells perfect for space applications. Germanium brings four key advantages. Superior conductivity. Electrons move faster in germanium than in silicon, meaning better efficiency. Infrared absorption. It captures light beyond what silicon can absorb, converting more sunlight into electricity. Extreme durability. It withstands rocket launches, deep space radiation, and extreme temperature swings. Radiation resistance. In space, high-energy radiation degrades electronics. Germanium holds up far better than silicon. So if germanium is this amazing, why don't we use it in everyday solar panels? Germanium is rare in the Earth's crust, with an average abundance of about 1.5 parts per million. That makes it far less common than silicon, but more abundant than elements like silver or platinum. Unlike major industrial metals, germanium doesn't form large ore deposits. Instead, it exists in trace amounts within sphalerite, zinc sulfide ores, and coal ash, making its extraction dependent on zinc and coal production. The discovery of germanium dates back to 1886 when German chemist Clemens Winkler identified it in the rare silver sulfide mineral argyrodite. Initially a scientific curiosity, its importance grew with the rise of semiconductor technology in the mid-20th century. Germanium was a key material in early transistors before silicon largely replaced it in consumer electronics. However, its unique properties still make it essential for fiber optics, infrared optics, and high-efficiency space solar cells. So how do we go from old scrap material and zinc residues to shiny high-tech solar cells powering satellites in orbit? Let's follow the journey from raw Earth to the outer space. Germanium doesn't come in pure chunks. It's a hidden element found in trace amounts within zinc ores, coal fly ash, and industrial scrap. To become part of a solar cell, it first needs to be extracted through smelting and chemical processing. While the exact steps can vary, here's a simplified flow sheet in a nutshell, outlining a common refining pathway. Separation from zinc and coal residues. In zinc smelters, germanium follows the gas phase and collects in dust and residues, while in coal combustion, it remains trapped in fly ash. These byproducts are processed to extract a germanium-rich concentrate. Chlorination to germanium. Tetrachloride. Germanium oxide reacts with chlorine gas, creating volatile germanium tetrachloride that can be purified through fractional distillation, removing impurities like arsenic, silicon, and iron. The purified germanium tetrachloride is hydrolyzed back to germanium oxide, which is then reduced with hydrogen gas, yielding metallic germanium. Zone refining. To achieve the extreme purity required for solar applications, an induction coil sweeps across the metal ingot, melting only a small section at a time. This method pushes remaining impurities to one end, which is later removed. The result? Germanium with impurity levels measured in parts per billion. But we are still multiple steps away from the actual germanium solar cell, so let's continue our journey. To function as the foundation of high-efficiency solar cells, germanium must have a precisely ordered atomic structure. Impurities or crystal defects would disrupt electron flow, reducing performance. That's why germanium is transformed into flawless single crystals using the Czochralski method, a process that ensures near-perfect atomic alignment. Melting and seeding. Ultra-pure germanium is melted, and a small seed crystal is dipped into the melt and slowly pulled upward while rotating. Crystal formation. As the seed rises, molten germanium solidifies around it in a perfectly ordered structure, forming a cylindrical single crystal. Wafer production. The crystal is sliced into ultra-thin wafers using precision diamond wire saws, then polished and etched to eliminate any surface defects. Without this step, the final solar cell would suffer from efficiency losses due to misaligned atomic structures or imperfections. Next, building the multi-junction solar cell. The heart of the process takes place inside a MOCVD, metal organic chemical vapor deposition reactor, a machine that deposits atom-thin semiconductor layers with absolute precision. First layer gallium arsenide. A controlled flow of trimethyl gallium and arsine gas decomposes at high temperatures, 650 degrees Celsius, allowing gallium and arsenic atoms to bond into a perfect crystal lattice atop the germanium wafer. Next, trimethylindium, trimethyl gallium, and phosphine react under precisely controlled conditions. Gallium-indium phosphide is formed. Now the multi-junction solar cell is finished. Each layer is only a few microns thick, yet they must be crystal perfect. Even the smallest atomic misalignment could disrupt efficiency. Once the semiconductor layers are complete, the solar cells go through additional treatments. Chemical etching and annealing. These processes refine the crystal structure and enhance efficiency. Passivation coatings, protective layers, are applied to prevent degradation from space radiation. Final assembly. The wafers are cut, polished, and integrated into solar panels. Throughout the entire process, the cleanroom environment is critical. After months of meticulous processing, a whisper-thin stack of semiconductor layers is now a high-efficiency solar cell. These cells will power satellites, spacecraft, and rovers, ensuring they can operate in the harshest conditions, where every photon of sunlight counts. Next time you look up at the night sky, know that some of the most advanced technology orbiting above began its journey deep underground as a byproduct of coal and zinc processing. If you enjoyed this deep dive into material science, don't forget to subscribe. What material should we explore next? Let us know in the comments.